Good morning, distinguished moderator, all participants of the Borobudur International Symposium and audience. My name is Gunawan from Universitas Pancasakti Tegal. Today, I will present our work entitled Deep Learning Models for Earthquake Magnitudes Prediction, a future research roadmap based on USGS data from Chile, Iran, and Java, Bali. Rather than proposing one single best model, this study introduces a research roadmap. The roadmap is designed to guide future deep learning studies on earthquake magnitude prediction using harmonized, publicly available seismic data from multiple regions. Background and motivation. Earthquake remain one of the most destructive natural hazards, especially in highly active regions such as Chile, Iran, and Indonesia. For earthquake early warning systems, rapid and reliable magnitude estimation is a crucial component. The earlier and the more accurately the magnitude can be estimated, the more useful the warning is for risk reduction. In recent years, deep learning has shown strong potential for analyzing seismic signal and predicting magnitudes. However, the existing literature is often limited to single regions, proprietary datasets, and ad hoc experimental designs, which makes it difficult to compare results or to generalize findings to other tectonic environments. This motivates us to think not only about models, but also about systemic research framework, research gap, and problem statement. The current landscape of deep learning in seismology faces several gaps. First, many studies rely on region-specific non-public datasets. These datasets are often poorly documented and cannot be easily shared or reproduced. Second, pre-processing steps, model architecture, and evaluation metrics vary wildly from one study to another. At the same time, public catalogs such as the USGS ANSS COMCAT are still underutilized for systematic multi-regional magnitude prediction. Because of this heterogeneity, different data, and different evaluation standards, it becomes very difficult to answer basic questions such as which model is genuinely more robust, or does a model trained in one region transfer well to another? Therefore, our problem statement is there is a need for a transparent multi-regional research roadmap that standardizes data usage, model design, experimental scenarios, and evaluation protocols for deep learning-based earthquake magnitude prediction. Aim and research questions. The overall aim of this study is develop a future research roadmap for deep learning models in earthquake magnitude predictions, based on harmonized USGS data from Chile, Iran, and Java, Bali. To achieve this aim, we formulate four research questions. Research question 1. Which input, representation, and features are most relevant for deep learning-based magnitude prediction? Research question 2. Which families of deep learning models should be prioritized for both waveform-based and catalog-based input? Research question 3. How should experimental scenarios be designed in order to assess robustness and generalization across different regions? Research question 4. Which evaluation metrics and validation protocols best support comparability and reproducibility? The roadmap is our response to these questions and provides a structured design space for future empirical works, data source, and study regions. Our roadmap is grounded in publicly available data from USGS ANSS Comprehensive Catalog, or COMCAT, covering approximately the period from 1970 to 2020. We focus on three seismically active regions with distinct tectonic settings. Chile, representing a major subduction zone along the Nazca South American plate boundary. Iran, characterized by complex collisional and interplate tectonics. Java, Bali, located along the Sunda megathrust, where subduction and volcanic arc processes dominate. From COMCAT, we extract core attributes such as origin time, latitude, longitude, depth, and preferred magnitude using moment magnitude where available. We apply basic event filtering keep only earthquake, removing duplicates and consider region magnitude completeness as a starting point. These steps create a harmonized foundation that can later be enriched with additional region informations. Conceptual framework of the roadmap. The slides present the conceptual framework of our roadmap. restructure the roadmap into 5 main components. 1. Harmonize multi-regional catalogs from Chile, Iran, and Java Valley. 2. Preprocessing and input representation designed including waveform-based and catalog-based options. 3. Selection of deep learning model families suitable for this representation. 4. Design of multi-regional experimental scenarios covering within region and cross-region setups. 5. Standardized evaluation metrics and reporting protocols to enable meaningful comparison. The intention is not to fix one particular model, but to define a coherent design space. Future research can position their work within this framework, making their methodological choices explicit and comparable to others' input representations. We propose 2 primary families of input representations. First, waveform-based representation. This involves the 3 components waveforms recorded at one or more stations. Signals are typically aligned with a P-wave onset and a fixed time windows such as a few seconds after P arrival is selected. Preprocessing may include best correction, detrending, bandpass filtering, resampling, and normalization across channels and stations. Such inputs are suitable for convolutional and attention-based models that learn rich time frequency pattern directly from the data. Second, catalog-based spatio-temporal representations. Here, the inputs are event-level features such as origin time, location, depth, magnitude, and, where available, focal mechanisms. We can construct contextual features, for example, the reason seismicity within a moving time window. These features can be encoded as a temporal sequence or spatial grids, making them suitable for recurrent networks or transformer-based models. Both families can also combine in a multimodal architectures, which we consider later in the roadmap. Deep learning model families. Based on this input representation, we outline several deep learning models families. For waveform-based data, convolutional neural networks, CNNs, are natural candidates as they can capture local pattern in time and frequency domains. In addition, recurrent neural networks such as LSTMs or GRUs can be used to model temporal dependencies, either directly on waveforms or on derived features. Transformer-based architecture are increasingly important due to their self-attention mechanism. They can integrate information from multiple stations and capture long-range temporal relationship more flexibility than a traditional recurrent models. For catalog-based inputs, we consider sequence models again, RNNs, or transformer that operate on sequence of events and spatio-temporal features. Finally, we highlight multimodal and hybrid models, which combine waveform data, catalog information, and classical seismological features. These hybrid knowledge data-driven models can leverage domain expertise while still benefiting from deep learning representation power. Experimental scenarios. To rigorously assess robustness and generalization, we propose 4 experimental scenarios. Scenario 1. Within region training and testing, here, each region, Chile, Iran, and Java Valley, treated separately. Model trained and evaluated within the same region, providing region-specific baselines. Scenario 2. Cross-regions transfer. In this scenario, a model is trained in one region, for example, Chile, and then tested in another region, such as Iran or Java Valley, without fine-tuning. This allows us to quantify domain shift and out-of-distribution performance. Scenario 3. Multi-regional joint training. All regions are combined into a single training set. We then evaluate both global performance and performance by region, investigating whether joint training improves generalization. Scenario 4. Domain adaptation and fine-tuning. Models are pre-trained on data-rich regions and fine-tuned on data-scarce regions. This is particularly relevant for countries with limited local seismic records but high seismic risk. Evaluation protocol and metrics. A key part of the roadmap is evaluation protocols. We recommend temporal data splits where models are trained on earlier years and tested on later years. The setups better reflects a real-time operational condition compared to random splits. We also suggest stratified sampling across magnitude bins to mitigate the strong imbalance between small and large event. For regression tasks, we propose standard metrics such as mean absolute error, root mean square error, and the coefficient of determination R quadrant. For threshold-based tasks, such as predicting whether an event exceeds a certain magnitude, we recommend accuracy, precision, recall, and F1 score. Importantly, we encourage researchers to report metrics per region, per magnitude bin, and per depth range, and where possible to include uncertainty estimates. This level of detail supports comparability, transparency, and reproducibility, contribution, and implication. This roadmap makes several contributions. From a methodological perspective, it provides a structured multi-regional framework for designing and evaluating deep learning models for earthquake magnitude prediction. It clarifies the space of input representation, model families, experimental scenarios, and evaluation protocols. From a scientific and practical perspective, it encourages this use publicly available data, such as USGS COMCAT, and promotes transparent and reproducible research practice. By enabling more systemic benchmarking, the roadmap helps the community identify which architecture and configuration are more genuinely robust across different tectonic settings. In the longer term, this work supports the integration of deep learning models into earthquake early warning and seismic risk reduction system, particularly in regions with limited data but high vulnerability. Conclusion and future work. To conclude, this study does not claim to introduce a single optimal deep learning model. Instead, proposes a coherent research roadmap that organizes future work on earthquake magnitudes prediction around multi-regional publicly available data. By leveraging USGS data from Chile, Iran, and Java Bali, the roadmap promotes the studies that are more robust, more comparable, and more generalized. It also designs to extensible to additional regions, new data types, and diverse application contexts. Future works includes empirical implementation and comparison of specific CNN, RNN, and transformer architecture under the proposed scenarios. The exploration of multimodal inputs, such as geodetic measurement and systematic analysis of operational constraints, include latency station outage within real earthquake early warning pipelines.